So let's call this lecture commonly used, bless you, negative feedback op-amp circuits. Okay. And I believe that all of you were made aware of these circuits in circuits one. But we're going to cover them anyway. And for what it's worth, on your first exam, some of the questions are going to ask you to identify them. So it will actually be a little bit more useful now than it was in circuits one. Okay. So all of these are going to be negative feedback circuits. And as I mentioned at the end of our class on Monday, whenever we have a negative feedback circuit, we can just use the ideal op-amp rule because the amount of error that's introduced is going to be so small. So these circuits will behave in this way, even if we just do if we did our full-on analysis using the practical op-amp model, or if we just used the ideal op-amp model. So the first one that we're going to talk about is a buffer amplifier circuit, okay? So let's call this guy the unity gain buffer. And in a unity gain buffer circuit, we're going to have something akin to this, okay? So I'm going to start, as per usual, by drawing my op amp. I'm going to choose to put the inverting input terminal on top and the non-inverting input terminal on bottom. So that's going to make the voltage at this node V minus, and the voltage at this node will be V plus. This will be our output node over here. I'm going to go ahead and draw my supply terminals. If I don't draw supply terminals for other ones, just remember all of these do require power, so they should all have an implied VCC plus and VCC minus connection, even if I forget to draw it. Okay. All right, so there's our basic op-amp circuit. Now I'm going to draw our feedback path. Okay. So in this particular circuit, our feedback path is typically established literally by just a section of wire that directly connects our output pin to our inverting input pin. Okay. And then we're going to apply our input voltage Vin as I'm just going to say it's a function of time here because it's probably going to be some time varying voltage generated by some sort of sensor or something like that here at the input terminal. And typically speaking, we don't use a unity gain buffer to drive a load. So I'm not going to put some load resistance connected between the output pin and ground. This is actually going to serve as the first stage of some larger amplifier circuit. So the output of this stage would actually be connected to the input of a secondary amplifier stage. And we'll talk about that when we talk about cascaded amplifier circuits on Friday, okay? So to analyze this guy, I'm going to apply op-amp rule number 1 first. So I can observe that no current is going to flow into this input terminal and no current is going to flow into this input terminal. By inspection, the voltage at the non-inverting input terminal is just going to be our input voltage. So I'm just going to make a note here that V plus, which will be equal to V minus, is just going to be Vin as a function of time. And since V minus is connected by wire to our output terminal, that means that our output voltage, V out, as a function of time, is just going to be the exact same thing as our input voltage. So if we define our closed loop voltage gain, AVCL, as the ratio of V out over V in, we very obviously get a gain of 1, which is why this is called a unity gain buffer, okay? Now, some of you may be asking yourself, well, what the hell is the point of an amplifier that has a gain of 1, okay? So essentially, it just replicates our input signal. This amplifier is used as the first stage in what are called instrumentation amplifiers, where you're taking a signal from some sort of sensor that probably can't produce a lot of power, and you're feeding it into this so that the power supply terminals of this amplifier circuit maintain that signal so that you can do things with it, okay? So this isn't something that's used by itself. It's used in conjunction with extra circuitry. This is essentially just a way to force your system to have a really large input impedance, okay? So that you can connect it to other things. So that's our unity gain buffer. So the next circuit that we're going to look at is this guy right here. So let's call this the non-inverting amplifier. This is literally the circuit that we looked at in class on Monday. So I'm going to do something similar here. I'm going to start with my op amp. Once again, I'm putting the inverting input terminal on top, non-inverting on bottom. So this is my inverting input pin with some associated nodal voltage of V minus, my non-inverting input pin with some nodal voltage V plus. Once again, got my output pin over here. Drawing my supply voltages. You guys are sniffly as hell today. I've heard lots of sniffling, not necessarily in this class, just generally speaking, it seems like every class I teach, several people have sniffles. Did you say they're diseased? Well, that is not nice. All right. So what I'm going to do in this guy is I'm going to establish my feedback path. But in this case, I'm going to use a resistor. Okay. So because I'm unimaginative, I'm going to call this resistor RF, where the F stands for feedback. So I will refer to this as just our feedback resistor kind of from here on out. Okay. I'm going to connect a resistor on the inverting input terminal over here as well, where the left leg is going to be set to ground. I'll call this resistor R1. And I'm going to apply an input signal V in as a function of time here. And I'm going to do this in purple. So I won't necessarily always drive some load with this circuit, but it is capable of driving a load. So I'm going to put a load resistance RL here. The reason why I'm putting it in purple, and I'm going to use that color for optional things, is because this circuit will behave essentially the same way, regardless of whether or not we drive a load with it, assuming that our load is significantly larger than the output resistance of the op amp itself, okay? So if the output resistance of the op amp is 25 ohms, we could drive a kilo ohm size resistive load here without any issues, but putting something on the order of like 100 ohms or so might not be a good idea. It will actually impact the performance of the device, okay? All right, so let me just note here RL needs to be much greater than R out for the amplifier. Okay. All right. So once again, I'm going to note that no current can flow into or out of my input terminals. By inspection, I think we can very easily see that the voltage at the non-inverting input, which will be the same thing as the voltage at the inverting input, is just going to be Vn as a function of time. And so now I'm going to apply Kirchhoff's current law at my non-inverting input node. Okay. So I'm just going to be adding this current and this current together. Okay. So that's going to look like Vn divided by R1 plus Vn minus V out divided by Rf is equal to 0. And with just a little bit of manipulation, which I'm not going to bother going through the algebra here because you can practically do it in your head, what you'll find is that our output voltage for this particular configuration will be equal to a resistance ratio 1 plus Rf over R1 times our input voltage Vn of t. And from this, then we can easily see that our closed loop voltage gain, AVCL, just the ratio of V out to Vn, will be 1 plus Rf over R1. So I want to talk a little bit about the name of this amplifier. Okay. So this is a non-inverting amplifier, and it's called the non-inverting amplifier for two reasons. Okay. So the first reason is that the input signal is applied on the non-inverting input side of the amplifier, right? So in this case, we have it connected directly to that V plus pin. We could also put a voltage divider network or something like that in between the input signal and that pin, and it would still be a non-inverting amplifier. Okay. Another reason why we call this a non-inverting amplifier is because our voltage gain is always going to be a positive quantity, meaning that if we put whenever our input signal is positive, our output signal will also be positive. Whenever our input signal is negative, our output signal will also be negative. You can notice from this gain that the lowest possible gain we could ever get would be 1, okay? So if our feedback resistance is very low, like a short circuit, and our R1 is very large, like an open circuit, we have a unity gain buffer. So this, the unity gain buffer is actually a special case of this particular amplifier configuration when we let RF go to 0 while R1 goes to infinity, okay? So this particular configuration applies some form of amplification. That's all it does. It makes our output signal equal to or greater than or equal to our input signal, okay? So now let's look at the non-inverting, excuse me, the inverting amplifier. So in the inverting amplifier, we're going to have literally this exact same circuit. The only difference that we're going to make, or the only change that we're going to make, is we're going to swap the location of Vn and ground on the left-hand side of the circuit. Everything else is going to be absolutely identical, okay? So let me just redraw this guy. Yeah, when I did the demonstration for those of you that took me for circuits 1, I literally just swapped 2 wires to change my non-inverting amplifier into an inverting amplifier because that's all it takes. And that lab is miserable, for sure. Or it's miserable when the students have to do it. It's not so bad when I have to do it because I, generally speaking, know what the hell I'm doing. So here's my non-inverting input terminal, my inverting input terminal, my output terminal. Here's my positive supply voltage and negative supply voltage. So once again, my feedback path is going to be established by some feedback resistor, R sub F. I'm going to have a resistor connected to my inverting input terminal over here to the left as well. It will once again be R sub 1. But instead of grounding this left-hand leg of that resistor R1, now I'm going to apply my input voltage here. And I'm going to ground that non-inverting input node like so. And this can be used to drive a load as well. So I'll throw an RL down here for good measure. And once again, anytime I draw a load resistor, it needs to be significantly larger than the output resistance of the op amp. Yes, sir.
All these are for negative feedback op amps. Is there a version of the ideal op amp rules for positive feedback op amps?
No. So a positive feedback amplifier isn't actually used to amplify the signal, right? We saw that the output saturates to either VCC plus or VCC minus. So there's really no need to have a set of rules because we know the output is always going to just be VCC plus or VCC minus. We just need to figure out what conditions make that happen, which is exactly what we did in those lectures. Yeah. So for what it's worth, if you look in your notes for the positive feedback amplifier, actually, I was thinking of the open loop amplifiers where I give you a specific input-output relationship for the inverting comparator and the non-inverting comparator. We didn't really do one of those for the positive feedback circuits, the Schmitt triggers, because really the thing that's causing the change is the upper trigger limit voltage and the lower trigger limit voltage. So comparing the input voltage to those values tells you whether or not you're going to have V out as VCC plus or V out as VCC minus. So, all right. So applying our op amp rule, noting that these currents are 0. By inspection, we can again see that the voltage present at the non-inverting input terminal is going to be, in this case, 0. And that'll be the same thing at the inverting input terminal. When we apply Kirchhoff's current law at our inverting input node this time, we're going to come up with the relationship 0 minus Vn. So I'm just going to write this as minus Vn over R1. Then we'll add the current flowing up through the feedback resistor. So that's going to be 0 minus V out. So I'm just going to write that as minus V out over RF is equal to 0, which can very easily be rearranged to find that our output voltage is simply going to be negative RF over R1 times our input voltage. And we then get a closed loop voltage gain of negative RF over R1. So this guy is called an inverting amplifier for reasons very similar to why the last amplifier was called a non-inverting amplifier. Our input signal is applied on the inverting input side of our amplifier. And our voltage gain tells us that our output signal will be of the opposite polarity of our input signal, meaning that whenever our input signal is positive, our output will be negative. Whenever our input signal is negative, our output will be positive. So with this particular amplifier, we can provide not only gain, so whenever RF is greater than R1, we'll see that our output is larger than our input, but we can also achieve attenuation, meaning we can make a signal smaller at the output than it was at the input. So we have a little bit more versatility here at the consequence, and I'm using this in air quotes because in an overwhelming majority of applications, the polarity of the output voltage is inconsequential. So we have a drawback, supposedly, of having an inverting system where the output is the opposite sign of the input signal. Okay. This particular topology is actually what several other amplifier systems are based on. So when we talk about differentiating amplifiers and integrating amplifiers in maybe 20 to 30 minutes, it's literally this exact same circuit, except that we replace one of the resistors with an energy storage element. Okay.
Help me remember the word attenuate. I feel like I've never remembered it. I was like a senior and y'all would say it. I'd be like, "What all the time."
Make it smaller.
Yeah.
Okay, so the next one that we're going to look at is going to be called a weighted inverting summing amplifier. And it is just a modification of this circuit. And the modification will be that we're going to have multiple input signals instead of just a single input signal. Okay. So weighted inverting summing. Ooh, goodness, that got away from me. Amplifier. All right, so starting with the basic op-amp circuit. Now I'm going to draw my supply voltages. Oh, I forgot to label my output voltage, my apologies. So here's V out. So I'm going to have some feedback path, RF up here again. I'm going to be grounding my non-inverting input terminal again. And then over here on the inverting input side, instead of putting a single resistor, for this particular example, I'm just going to put 3, but you could technically do more than 3 if you wanted to. You just need to make sure that you're not going to push so much current through this system that it burns the op amp out. Which, if you're using kilo-ohm size resistances, should practically never be an issue. So I'm going to call this resistor on top R1, the resistor in the middle R2, this resistor R3, and we will have 3 different input signals. So I'll call this one V1, this one V2, and this one V3, like so. And once again, we could, if we were so inclined, drive a load with this guy. All right, so let's analyze it really quickly. We know that no current can flow into our input terminals. We can very easily see by inspection that the voltage present at our non-inverting input terminal is going to be 0 volts. And we know that that will be the same as the voltage present at the inverting input terminal. So I'm going to write that down as well. And now we're simply going to apply Kirchhoff's current law at our inverting input node again. So we're going to be adding this current, this current, this current, and this current together. So that's going to look like 0 minus V1 over R1. So I'm going to write minus V1 over R1. And similarly, we'll have 0 minus V2 over R2 and 0 minus V3 over R3. So those are all three of our currents flowing to the left. To the right, we have 0 minus V out over RF. So I'm going to write that as minus V out over RF. Set this equal to 0, and then rearrange. And in rearranging this guy, we're going to see that our output voltage is going to be negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. So this guy is called a weighted inverting summer. And the reason that it is an inverting amplifier is because we can see that from this input-output relationship, we have a negative sign. So if all of these inputs are positive, then the output will be negative, that kind of thing. It is a summing amplifier because on the right-hand side here, we can see that we have our input voltage 1 plus V2 plus V3 added together. And it's weighted because each of those input signals can be scaled by a different amount or a different weight, right? And it's just going to be the feedback resistor divided by the resistor connected to the input signal, okay? So the signal V1 has a weight of RF over R1, V2 has a weight of RF over R2, et cetera, et cetera, et cetera, right? If those resistors R1, R2, and R3 were of the same value, then they would all be scaled by the same amount, which means we would no longer have a weighted inverting summing amplifier. We just have an inverting summing amplifier because they all have the same weight to them. Okay. So you guys have probably interacted with a inverting summing amplifier before. How many of you have stepped on a digital bathroom scale? Practically all of you, okay? So I'm going to draw a really terrible picture here. So my bathroom scale looks something like this. It's like a square thing. And then it's got a little deal here that tells me where to put my left foot. And it's got a little deal here that tells me where to put my right foot. And underneath here, there's what's called a load cell. So there's one at the front of your foot, one at the back of your foot, another one here, and another one here. And each one of these load cells generates a small, so on the order of millivolts of voltage, amount of voltage that depends on the amount of weight that each one of those cells sees. All of those sensors connect to the input signals of a weighted inverting summer like this, and they're all scaled by the same amount so that when you add all of those signals together, it tells you your weight. For what it's worth, the weigh stations that you see leaving or entering a state by an interstate highway is based on effectively the exact same thing. For my guitar nerds here, if you have a practice amplifier so that you can plug in like let's say your phone so that it can play a song as well as your guitar. It uses this to do that same thing to where the output is actually the signal from your guitar and your phone at the same time. And then usually it would have a potentiometer that lets you blend so you can make the guitar signal louder or the audio signal louder. But anyway.
There's a potential where there would be equivalent to changing V1, V2, or V3.
So yeah, so it'll change the weight of one of the signals, right? So you would put the potentiometer. So this guy might be a potentiometer. The signal for potentiometer is just a resistor with an arrow through it, letting you know that that resistance changes. Okay. So you can change the weight by adjusting that potentiometer as well. I wasn't particularly intending to. That being said, we can knock that out really easily if you want to, just as a quick aside thing here.
I was talking about like in the course.
Yeah, no, that's what I mean. Yeah. So like, I don't know that we ever really cover what a potentiometer is. We just kind of, yeah. But let's talk about it. Let's add a little something that wasn't covered in circuits one just for the hell of it. Let's make sure you guys are paying for something this quarter. All right. So I'm going to scroll over here to the very last page. We're going to talk about a potentiometer really quickly. This will be an aside, but you know, why the hell not? Okay. So potentiometers. Okay. So a potentiometer is a variable resistance. Okay. Now, actually, there are two different types of variable resistors that you might see, potentiometers and rheostats. A potentiometer is a 3-terminal variable resistor, and a rheostat is a 2-terminal variable resistor. You can use a potentiometer as a rheostat, and in fact, they've almost stopped making rheostats because the overwhelming majority of people just use a potentiometer for it. Okay, so we'll talk specifically about a potentiometer here. I'm going to pull up a picture of one just on Google, and then I'm going to draw something real shitty. Okay.
So are volume knobs to potentiometer?
They are indeed. So get rid of this dumb thing. Get rid of that too. Nope, I don't want to run a virus scan right now. I want to teach my class. Jesus. Okay, so we're going to look at this picture right here. Okay, so we've got, close that. So this knob is moving this wiper along this resistive path. And then we have 3 different terminals, okay? So now I'm going to try to draw a simple picture that we can kind of understand here, okay? So here's one terminal. Here's another terminal. And I'm going to draw kind of a resistance thing here, indicative of the resistive path, okay? So if we measured the resistance between these outside terminals, it's always going to be a single fixed value, okay? So you can buy a potentiometer, like a 10K potentiometer, 100K potentiometer, mega ohm potentiometers, all of that kind of stuff. That's telling you what the resistance is between the outside terminals, okay? But then we also have that wiper terminal, okay? So we could, I'm going to draw it like this in the middle, okay? So the resistance between here and here is going to be, let's say, R nominal, okay? And then if we measure the resistance between the leftmost terminal and that middle terminal, that resistance is going to depend on where the wiper is. So I'm going to call the resistance measured between here and here R wiper. And so the resistance measured between here and here is just going to be R nominal minus our wiper, because these guys, but if we measure between the left and the middle and add that to between the middle and the right, it should add up to be the nominal resistance, okay? It's literally just a carbon path that has a particular width and a particular thickness so that it has some fixed amount of resistance. And as you adjust that knob, it moves that wiper around so that you see less of that carbon strip on one side and more of that carbon strip on the other. That's all a potentiometer is. I saw a YouTube video, maybe it was a couple of weeks ago. And I'm about to bore the shit out of everybody that isn't into guitars, but that's okay. You should be into guitars if you're not. I saw a YouTube video fairly recently of a guy that was taking apart his potentiometers and literally cutting a small section out. So they was breaking his potentiometers up into two discrete resistances that you could vary, so that he was using those as, like, depending on where your potentiometer was set, it could be two different types of filters so that you could get like weird effects and stuff with that. So that was a pretty interesting thing. I'd never thought about doing that. But if you take it apart and you just literally use an X-Acto knife to remove some of that carbon strip, you get two smaller resistors that are both variable. So I thought it was kind of interesting. What more would you care to know about a potentiometer?
Get through that.
Okay. Oh, actually, I guess one last thing. You can get potentiometers that have a linear taper, meaning that it's just a straight relationship. And then you can get ones with what are called an audio taper or a logarithmic taper. So audio taper and logarithmic taper are the same thing. They achieve that by literally just making the copper tray or the carbon trace get wider as you go across the wiper, so that you'll get like a lot of. So like if you have like a 500K audio taper pot, like with a linear taper, you'd be at 250 kilo ohms if you were exactly in the middle. With a logarithmic taper pot, you might be at like 100 ohms when you're in the middle, and then it will exponentially increase to the full value when you get closer to the far side of the wiper. But anyway. So if you're going to use a potentiometer, and I've even seen graduate students make this mistake, realistically, you probably don't want to have both of the outside terminals actually connected to anything in your circuit, because it's just going to look like that nominal resistance. So you really only want to use two of them usually. And it's a question of, do you want the resistance to increase when you turn the knob clockwise, or do you want the resistance to decrease when you turn the knob clockwise? Jacob asked if this is how you get like a volume control. Absolutely. It's also how, well, we don't have like analog radios really anymore, but this was the control for changing this radio station when you had old school radios and all of that kind of stuff as well. So, all right, potentiometers covered. All right, so let's talk about a differencing amplifier here, right? So this amplifier allows us to add signals together. I guess before we move on from this, I should say you could make a weighted non-inverting summing amplifier if you wanted to as well, but the math on that just gets really gross really fast. So usually, if you wanted to get a positive input signal out of this system, you would just take the output of this, run it into a second stage that is another inverting amplifier that will flip that polarity back to positive. So anyway. All right, differencing amplifiers. So this is an amplifier that has multiple input signals, but this time we're going to put one input signal on the non-inverting side and one input signal on the inverting side. Okay. So we'll do something akin to this. Starting with my op amp again. So this will be V plus. No, sorry, that'll be V minus. My apologies. So we're going to have our feedback path up here again. And I'm going to call our feedback resistor R2 here instead of RF, and you'll see why in a moment. I'm going to put a resistor R1 here between the inverting input node and one of our input signals. And I'm going to call the input signal that's applied on the inverting side V1. Now I'm going to put a voltage divider network on the non-inverting input side of the amplifier. So I'm going to have some resistor here. This guy needs to be R1 as well. And it is important that this R1 and the R1 on the non-inverting side or the inverting side are the same resistor value. Okay. So we need matched resistors here. And this resistor is going to be another R2. I'm going to put a second input signal that I'll call V2 over here. And we could be driving some load with this guy, so I'll put a resistance RL down here. So there's a couple of different ways that we can analyze this circuit. And I'm going to actually choose to analyze this circuit using superposition because it will let me avoid a little bit of math that the algebra can get a little bit gross if I don't pay enough attention and I'm sleepy, so I feel like I might not be up to it for today, okay? So if we were to look at this circuit where, so let's say when V2 is off, okay. So if we were to ground out V2, what voltage would be present at the non-inverting input terminal? Zero volts, okay? So let's just imagine that that V plus terminal was connected directly to ground then, since we know that there's 0 volts there. What kind of amplifier would that be? So we have an input signal applied through some resistive network on the inverting side of the amplifier, right? So it's literally just the inverting amplifier that we talked about a couple of minutes ago. Well, we know what the input-output relationship for that is, okay? So when V2 is off, we should see that V out as a function of time, and I'm going to put a prime here since we're doing superposition, so this is just a portion of our output signal, is going to be equal to negative R2 over R1 times our input signal, which is V1 of t. Okay, are we all okay with that? So now let's look at what happens when V1 is off. Okay. So I already mentioned this a moment ago, but the voltage that's applied at or the voltage that we'll see at our non-inverting input terminal is going to be based on that voltage divider ratio, right? We know that no current is going to flow here. So that means essentially that any current that's being supplied by our input signal V2 is going to flow through this R1, and then it's going to flow down to R2 on its path towards ground. Okay. So we have a simple voltage divider there. So I think pretty obviously V plus in this case is just going to be V2 times R2 over R1 plus R2, just using voltage division. Okay. So I'm going to write that down really quickly. So V plus will be V2 times R2 over R1 plus R2. Okay. And now I need us to figure out what the output voltage will be from this contribution. Okay. So imagine that we had a voltage source supplying that amount of voltage directly connected to that V plus pin. When V1 is grounded out, well, that's just a non-inverting amplifier. Okay. So we would have 1 plus R2 over R1 times that voltage V plus. So I'm just going to write this out as R2 over R1 plus R2 times V2. Are we all okay with that? So what I'm going to do now is I'm going to manipulate this a little bit further before we add these two output signals together. Okay. So I think, and please tell me I'm wrong if I'm wrong, but I'm not wrong, that I can write that 1 right there as R1 over R1. And that would allow me to rewrite this bit as R1 plus R2 divided by R1. Everybody okay with that? Okay. So I would have R1 plus R2 divided by R1 multiplied by R2 over R1 plus R2 times this signal V2. And I think we can all see that this R1 plus R2 in the numerator is going to cancel this R1 plus R2 in the denominator, leaving us with just R2 divided by R1 times V2. So now, when I consider the case where both input signals are on, my output is just going to be a combination of those two outputs. And sorry, this guy should have been double prime. My apologies. Okay. So I'm just going to do this over here. We can say that V out as a function of time is going to be our output signal negative R2 over R1 times V1 plus our output signal when V1 is off, which was R2 over R1 times V2. And I'm just going to algebraically rearrange this by pulling out that common factor of R2 over R1. And I'm going to put the V2 on this side, which has a plus sign, and I'm going to put the V1 on this side, which has the minus sign. And so we can see that the output signal of this particular configuration is just the difference of our input signals, V2 minus V1. So the one on the non-inverting pin gets a plus sign, the one on the inverting pin gets a minus sign. And then that difference is scaled by the ratio of those resistances. So if we wanted the output to purely be just the difference of those two signals, we just need to make R1 and R2 equal to each other. So we've now figured out how to add signals together and subtract signals from each other, okay? We can't do multiplication or division yet. So now we're going to talk about other mathematical operations that we can do with just a single amplifier. And that will be actually the calculus relationships of differentiation and integration. So let's start with what I hope will be a differentiating amplifier. I say I hope because I can never remember which one the capacitor is supposed to be in the feedback position is. So I might have to go back in here and change this to an integrating amplifier after I do the derivation, but I think I can remember. So differentiating amplifier.
For differentiating amplifier, it's like the capacitors on the inverting.
Yeah, I thought so. Yep. And I believe Miss Ward made her class design a differentiating amplifier circuit last quarter, right? I wasn't that mean.
Oh, yeah.
All right, so let me label my terminals here. So this will be V minus, V plus, VCC plus, VCC minus. So my feedback path for this amplifier is going to be established by a resistor. So I'm going to call that R sub F. And I'm going to replace that resistor R1 that we saw with our inverting amplifier with some capacitance C. And I'm going to explicitly draw my input signal as a voltage source here, and it'll kind of help us with one part of our analysis. So this will be Vn as a function of time, and I'm going to apply ground directly to my non-inverting input node like so. So one other thing I'm going to do here, and I'll do this, I guess, in green. I'm going to say that this is the polarity for our capacitor voltage, so positive polarity on the left. And this will be the direction for our capacitor current, IC of t, like so. And just to remind you guys of the relationship, we should be able to say that IC of t is simply C times the derivative of VC of t. Okay. We'll use that here in a couple of moments. This guy can also drive a load, so I'll just throw a load resistor RL down here for what it's worth. So we're going to do basically the same analysis that we've done in every other one of these circuits, but we might have to make some very, very slight changes, okay? So first, I'm going to, again, observe no current can flow into or out of our input terminals. By inspection, we can see that the voltage present at our non-inverting input terminal is 0. And this will be the voltage present at our inverting input terminal as well. So I'm just writing that down here. Now I'm going to apply KCL, but I'm going to do it slightly differently than how I've done it previously. Did I use green on all of those? Yeah, I did. Okay. That's fortuitous. So I'm going to add that, or excuse me, I'm going to say that that current IC is flowing in to the inverting input terminal node. And it's going to be equal to the current that's flowing out. Okay, so it's still KCL. I'm just doing it slightly differently. So I'll have IC of T will be equal to 0 minus V out over RF. So that's minus V out over RF, like so. And I can, I think, very obviously rearrange that to say that my output voltage here is just going to be negative RF times my capacitor voltage. Are we all okay with that? So now I'm going to substitute in that relationship for capacitor current. So I'll have negative RF times C times the derivative of my capacitor voltage. And I think it should be pretty easy to see that the positive polarity terminal of my input voltage source is at the same node as the positive polarity terminal of my capacitor voltage. The negative polarity terminal of my input voltage source is at ground, and the negative polarity terminal of my capacitor voltage is at a node that has a voltage of 0, which we would call a virtual ground. And so from that, I can infer that my capacitor voltage and my input voltage are the same quantity. So I'm just going to replace VC here with VN, giving us the relationship. V out is negative RF times C times the derivative of our input voltage with respect to time. Okay. So this is a differentiating amplifier. Okay. For what it's worth, this is used in control systems as well to perform derivatives and all of that kind of stuff. In a communication system, I believe this is a high pass filter. Okay, and we'll talk more about filters later on in this class. Just as another quick aside here, I chose to realize this differentiating amplifier with a capacitor. We could also create a differentiating amplifier with an inductor, but the inductor would need to be in the feedback position, and the resistor would be down where the capacitor is. Okay. The reason why you don't very regularly see differentiating amplifiers that use inductors is because the tolerance of an inductor is usually very large compared to the tolerance of a capacitor, meaning that there's a lot of variation when they're manufactured. So if you want consistent results, you would use a capacitor. The last amplifier that we're going to talk about today is the integrating amplifier, which is going to be this exact same circuit, except we're going to swap the position of the feedback resistor and the capacitor. So I'll do that down here on this last page. I'm sure that's where I learned it from. As long as I don't start talking about bubs.
You all see maybe in the power lab, there's some light bulbs, but he'd be like, all right, we're just gonna turn on 3 bulbs now. That's what he said.
Yeah. I think we're going to get out of here a little early if you want to let them into the old power lab just to see the light banks.
Awesome.
Yeah. He loved to knock off early, that's for damn sure.
All right, let's just get out of here.
Yeah. All right. I'm not as nice as Dr. Cox. We've still got a little bit more to do.
Similarly, for a integrating amplifier using an inductor, it would just be.
Yep. For what it's worth, I believe in a homework problem, I will make you guys derive the relationship for one of these circuits that has an inductor in it. But you can follow this derivation pretty straightforward. Excuse me. All right. So let's see, this will be V plus, V minus, V out. VCC plus, VCC minus. So I think I mentioned it a moment ago, but in this case, our capacitor is going to be in our feedback position. So I'm going to call this C sub F. We're going to have a resistor here. So this will be, let's just call it R. Our input signal is going to be applied over here on the left-hand side of that resistor R. And like we had earlier, our non-inverting input pin is going to be connected to ground. Like I did in the previous example, I'm going to choose to define the polarity of my capacitor. So I'm going to put positive polarity on the left. And then this current right here will be our capacitor current IC of T. To remind you guys, in case you have forgotten, the voltage drop across the capacitor for a known current can be written as 1 over C times the integral. And I'm going to do this integral from negative infinity to our time of interest. The reason why I'm doing the integral from negative infinity to T is so that I don't have to do extra math to take into account the initial condition for any voltage drop that's already across the capacitor, instead of just me saying it's going to be 0 or forcing it to be 0 by putting a resistor in parallel with that capacitor, which would technically make the analysis harder. I'm doing it the lazy way and just saying we're integrating from negative infinity. Okay. All right. And so it's going to be 1 over C integral from negative infinity to T of IC of T prime dt prime, where those T primes are just dummy variables representing time, since we have the variable T in the limits of our integration. I don't want to use it twice. Okay. All right. So starting our analysis, we can see that from the ideal op-amp rules, there's no current flowing into our input terminals. The voltage at our non-inverting input terminal V plus is 0. So that means the voltage at the inverting input terminal is also 0. So now I'm going to do KCL again. I'm going to do it the same way I did a moment ago. So we're going to have the current flowing into the node will be equal to the current flowing out of the node. So that's going to be Vn minus 0 over R. So that's just Vn over R is equal to IC. Okay. So we have a little bit of a problem here, in as much as every other time we've applied KCL at our inverting input node, we've had a term for V out, and we don't have one in this case. So we're going to have to get a little bit creative here. So I'm going to draw something here to kind of help us figure some things out. So our output voltage, V out, is a nodal voltage, meaning that it is measured with respect to ground. So I've explicitly drawn that down there, okay? The reason why I've drawn it that way is so that we can see that the positive polarity terminal of our capacitor voltage is at a node that has a voltage of 0. And the negative polarity terminal of our output voltage is at ground, okay? The negative polarity terminal of our capacitor voltage is at the output node, and the positive polarity terminal of our output voltage is at the output node as well. So essentially, V out and VC are the same voltage, just of opposite polarity. So I can write that V out is just negative VC, okay? So if we say that V out is negative VC of T, and then we substitute in our relationship for the capacitor voltage, excuse me, we'll have V out is equal to negative 1 over C times the integral from negative infinity to T of IC of T prime. And now I'm just going to substitute in my relationship for IC of T. So since that resistor is a constant, I can pull that out of my integral, leaving me with negative 1 over R times C sub F times the integral from negative infinity to T of Vn, like so. So our output signal is a scaled version of the integral of our input signal, but we also have a change in polarity. This is also a fundamental building block of control systems. So you'll learn about PID control, proportional integral differential. I is this guy, D is the one before. This is would be, I believe, a low pass filter in a communication system. I might be mistaken and have gotten the low pass and high pass backwards, but I think I'm right and we'll sort it out later. Yeah.
Jacob, I think Jacob asked a similar question, but I was wondering, so for the differentiating amplifier, you could essentially just replace that capacitor with an inductor and get an integrating amplifier?
So with this integrating amplifier, if I put an inductor in the position of the capacitor, I should get a differentiating amplifier. With this amplifier up here, if I put the inductor in place of the capacitor, this should be an integrating. So they should do the opposite mathematical operation. And the reason why they should do the opposite mathematical operation when you just switch them out is because they have the opposite relationship, right? So the IV relationship, the derivative-based relationship for capacitor is going to be the same thing as the integral-based relationship for the inductor. So yeah.
You typically only see capacitor integrating?
Correct. For the exact same reason. You just don't really use inductors to do integrating or differentiating amplifiers in practical circuits because, like I said, there's a lot of tolerance issues. Yeah. All right. I am done ranting about different op-amp circuits with you guys for today. So I'm going to kill the Zoom and then I'm going to go unlock the old power lab so that Ashton can show you Bubs if you're interested.